some of the questions some use curly braces, right? It doesn't matter what notation you have, as long as we have a system that takes an input and then produces an output and that they have a sense of definition. So we are going to use this box mostly to represent a system. So we have an input, and we're going to use an arrow to indicate the flow of the signal. So X of t goes into the system, so we have the arrow into the system, and whatever the system does to it, that's what we're going to get at the output. And we call it y of t. So, are you guys currently studying op-amps in electronics?
No.
No.
We're talking about electrons.
Oh, still?
Yep.
Orbitals.
We know a whole lot about silicon, so we're good.
So, then you're going to be behind during the labs, right?
Yeah.
As always.
That's,
We're having fun. It's okay.
that's what counts, right?
Yeah.
Yeah. Having fun is good. Alright, so, and sometimes, instead of having X of t, they will just drop the independent variable. Right, they will just drop the t. Right, so, for example, if I go back to the slide for the continuous time, close this. Instead of having y of t, you just call it y, and instead of having x of t, you just call it x. Right? So this notation is understood. We can choose to draw. This is just a notation. Okay. So we are going to talk about continuous time systems and discrete time systems. So we did talk about continuous time signal and discrete time signal. Okay? So let's take, well, if you guys are not doing op-amp, then thought about giving an example using op-amp. Well, but you know voltage division, right? Okay, so let me give you an example. So we have the input, we call it voltage. And let's say we have R1, and then we have R2, and the voltage here is to be R2 of t. So I'm interested in that, so I call it y of t. Right? So whatever we're interested in, we call it the output. Right? So here I wanted to calculate the output voltage, so I call it y of t. Now, can you help me compute y of t? Can we compute the voltage across the resistor? R2? So what is that? R2 over R1 plus R2 times x of t. That makes sense? So this is a constant, isn't it? Right? We call it C. So that means it's C x of t. So in this case, y of t equals to C x of t. For this particular example. Now, can C be bigger than 1? this case, when we're dealing with positive resistances, C cannot be bigger than 1, so this is called what? Attenuation. Right? So you take the input, you decrease the amplitude to get the output. Right? Kind of attenuate the input. So the book talked about that, right? That's called attenuation. But our condition, we can have amplification. Amplification means the A is bigger, right? The C, the constants. So let's say you put in a voltage, that's this. Oh, I think I need to put the setting of my own notes. And I will amplify to get something that will kind of look like this. Right? What can you use to do that?
Up it.
Up. Right? You can only use active devices to do this. Right? You have to have a source of energy into the system to be able to amplify. So if you have passive components as a resistor R1 and R2, there's no way you can amplify. Well, if you do, then let me know. We can make money. So that's right. So to do that, we need to have an active device. So that active components, we can take an external power and then amplify the signal. So to be able to do amplification, we need to use active component. So we need active component. So while you're not going to be asked to do any of talk about any of this, but I think because we're dealing with systems, you have to understand this stuff when you put them together in the lab. Okay? Right, so as we said, if you take an input, x of n, multiply that by constants, you get an output. This is called amplitude scaling. Right, so that means you're only changing the y-axis, the y component of the signal. You're not changing the time component of the signal. So last time we did talk about time scaling, where we can compress in time or we can expand in time. But here, we're only affecting the amplitude. Right? So when you multiply a signal by 2, for example, then the amplitude is going to be multiplied by 2, but the time axis is not affected. Okay, so I was giving you a differentiation, a system as a differentiator. Right? So you take an input, x, and you differentiate. I'll give you the output. So if the input is current, what do you think a differentiator, what component can we use to get the voltage here, which is the differentiation of the input? Inductor. Right? Inductor is the voltage is L di dt. The I is the current. Are you with me? Right? So we can take this inductor as a differentiator. Right? Because the input that we apply to it is current. Now, but then if I wanted to integrate to get the output, we call it integrator. Okay. So, let's say that I have still a current source. So what are the components that I have there? So the input is X. But what is the component that I can put in there so that I'll get the voltage, which is the integral of the input? Passive, right? Because the current through the capacitor is, well, let's do the voltage. So V is the integral of the current, right? So, well, you know that I is C dV dt. Are you with me? So to find the current, to find the voltage, V is integral from negative infinity to T. I C of tau tau. So this is called, anytime you have integral from negative infinity to T, what is it called? I think I mentioned this last time. Running integral. So this is called running integral. Okay? So this is an integrator. So put a capacitor there. We apply current. Yes?
Wouldn't it be 1 over C integral of negative?
Yes, I was making C equal to 1. Okay, so let me put it in C. Okay, so, thank you. All right, so the voltage is just the integral of the current. So in this case, we call it an integral. So there are two things that I want you to take away from this. What is a running integral? You have to remember it because you see this in questions. And you know, what is an integrator and what is a differentiator? So the input now need to be current. It could be voltage, right? Then we're talking about a different component. Are you with me? Right? So if the input was a voltage, right? So if I have a voltage here, and I want the current I to be the integral of the voltage, what component should I use? Inductor. Right. So it kind of depends on what you have as an input, right? That will tell you, you know what. So these are very simple examples, right? One component example. In real life, you never see an example like that's an inductor, and then you apply voltage to some constant, right? Inductors are made with coil, so it has some resistance, right? So if I wanted to be, you know, correct, I should have to put a resistance here with it. Right? But for the sake of this example, I'll just make it ideal. Inductor with zero resistance doesn't exist. Okay, so let's apply. So this is an input X. We wanted to run this through a differentiator. So that's the system. That's what is being done to the input, and then we want the output Y of T. So when we differentiate this, what do you think we are going to get? Anyone? I know you guys know this, because we've done it before.
The impulses?
Okay? So let me insert some space here. Who was that? John Johnson? Okay. Let me insert some space here. So for the quiz, we are going to solve similar examples just to refresh you before we take. Okay. I want to make sure that the weekend doesn't spoil everything you studied for the quiz for last week. So we're gonna review, we're gonna solve a few examples before we take the quiz. Make sure that the average of the quiz is better than the average of the practice quiz, which is 80 something. I want average more than 90 for the quiz one. So only 2 questions.
Uh-oh.
I'm gonna throw a force in 50-50, right? Well, you see for yourself, right? So, right, this is the first quiz, right? So, I like to keep my hopes very high. Alright, so, when we differentiate this function, what will you get? Yes?
Drawing it in there. Oh, sorry, man.
You kind of go in the air, I don't know.
Yeah,
Can you,
see?
can you help me?
Okay, no.
Alright, so what do we do?
Good question.
Okay, Jackson, what do we do?
Oh, you have the answer.
The inputs are 2.
Yeah.
Okay, I'll agree with that. So let me double the axis. Plus 1, 2, 3. So the first impulse happens where? 1. So what is it pointing upward or down?
It's gonna point
Okay, like that. And what is the area? 2. Right, because the transition is 2 units. Are you free? Okay. Now, so what about 2? 2. It goes down by how much? 3. Right? So the transition is what, 2 here and 1 here, so the total is 3. Which pointing down, so this is -3. Are you all free?
Yeah.
So you guys were pretty good in 2254, so I expect that. What about at 3? By 2. Well, we're having the quiz is even simpler than this. Yeah. So, I want to make sure that I don't go home sad today. I'm tired of it. Alright, so. Now, so so can we write the expression of y at t equals or equal to?
dy dt?
2, yeah. 2 delta
T minus
t minus 1.
minus 3 delta T minus 2
Thank you.
Wait, I thought he wanted the derivative.
plus 2 delta T minus 3.
Do you all agree with that?
Yeah.
Thank you. Very good. So, well, the first question that quiz has something to do with impulses, but we're gonna do that. So that's the plot. So any questions? Right, so this is -3 here. This is 2. And that is now let's talk about interconnection of systems. So we might have systems that are connected together. So the first one is when you have systems connected in series, from this. So serial connection or cascade. Are you clear? Now, when you see series, so most of the time you don't see series, you see cascade. When the system are connected in cascade, that means they are connected in series, right? So during an exam, a student called me on the side and said, what is cascade again? I said, that means series. Right? Well, the thing is, later on, you're going to notice that when we talk about systems that are connected in series or cascade, if you don't know the properties, then you won't be able to compute what you're asked to compute. Right? So when it says serial connection, that means the system are connected in series. That means the output of the first system becomes the input of the second system. Okay? So whatever I do to this, so let's say that I give you this. So let's say this is a differentiator. So the first system is going to take the input and differentiate that input to give you y. So let's say the second system is just an integrator. What do you think we're going to get the output? X of t. Right? So whatever we did to the signal on the first system, we cannot remove it so we differentiate and we integrate. What we're going to get is x of t. This is just an example. Okay? So in communication and signal processing, there's something that's called equalizer. And it's a system that will be cascaded with its inputs. So this system could be anything, right? And the second system could be anything. Right? So the only thing you can take away from this is that the output of the first system becomes the input of the second system. Okay? So if the first system differentiate the input and the second system also differentiate the input, what do we get? Differentiate twice. Right? Okay. Now, systems can be connected in parallel. Right? Parallel connection of systems. So what are the applications? So one of the applications, because something that I've did in the past, it's called system identification. So let's say I give you a system and you're only told that the system is linear and time invariant. So let's say for now you don't know what that means. So you take it, so let's say that's a black box. I just hand you the system, you have no idea, you have no clue how the system was made. Okay? And then you try to figure it out. You try to reverse engineer the system. So you can just take it to the lab and you can apply a bunch of input. Right? It's not just some random input. There's a process of doing this. And then what are we going to do? Instead of adding, I am going to subtract the output of the system. So let's say this is the black box. And I'm trying to figure out. So what I will do, I will make a system that has no clue how the black box was made. So because I'm taking the difference, this becomes an error. Right? The difference between the two. Right? And I use that and feed that back into systems 2. And I'm going to adjust the weight of systems 2 until the error is equal to 0. So when the error equal to 0, that means this system matches this system exactly. Right? They have to be the same for that to happen. So then, without knowing anything from system 1, I have a copy of system 2 that I know exactly how it's made. And that tells me how this system is made. Right? This is called system identification. So those who are going to go into controls, maybe signal processing area, that concentration, you might come across some of this later on. Alright, so systems that are connected series and parallel, a combination of series and parallel. So we have an input x of t, and so as you can see, system 1 and 2 are connected in series on there. And the series combination is now connected in parallel with system 3, right? And the output of this branch and this branch are added together here, and that becomes the input to system 4. And then we're going to learn later on how to simplify all this down to one system. Okay. Now, let's talk about feedback systems. Feedback systems are the most important systems that you see. Now, so can you give me an example of feedback system?
Here, David Bar.
So let's say
Cool.
when you're walking, right? So let's say you want to get out of this room. Your eyes are giving you feedback where to go, right? So let's say you just close your eyes, start walking. What's going to happen? You're going to hit a wall, right? So your eyes, they kind of guide you, right, to get out. So, well, I think an example that's appropriate is a cruise control of your vehicle. So let's say that you're driving down to where? Atlanta, for example. Yeah, at some point you felt tired, and then you put the vehicle on cruise control. Okay? So what happens? So before this thing kicks in, let's say that I know the maximum speed of that highway. Right? Obviously, you're driving. So you're gonna set that speed. So R here means the reference. That's going to be the reference input. R of t will be the speed that you set for the vehicle to, and then what is going to happen? You have a controller that constantly check the error. So this is the vehicle. So this is your car. We're going to measure the actual speed that the car is moving at. And then we're going to compare that to the reference input. Let's say you have 50 miles per hour. So it's going to take the input, it's going to calculate the output, and take the difference between what you measure, I call it Y measure, and the reference input. When the error is equal to 0, that means you're moving at the reference input, there's nothing to do. But when the difference is not 0, that means you're either speeding up or you're slowing down. Right? So when you slow down, the controller is gonna kick in to make sure that you track the reference input. And then if you're going beyond the speed that you set, then the controller is gonna send a signal to slow down the vehicle. Okay? So without feedback, there's no way you'll be able to do that. Right? So the cruise control of your vehicle is actually using feedback. Now, so this is where the fun begins. The properties of systems. We call it basic properties. And I'm going to give you 5 definitions And I want you to understand them, don't memorize them. Because they're going to come back very often. And if you understand them, then you always going to be able to solve those questions. So, there are 5 properties, there are 6 of them, but you're going to be responsible for 5. One of them is kind of tedious for a student of this class to prove, from what I've seen over the years. So I just give you the definition for your reference, because if you take analog and digital communication, you might see it there. But I will now test you on that question, on that problem. So the first one is when the system has memory or not. Right, system has memory or not. Okay, so if it doesn't have any memory, we say that it's memoryless. Right, so memoryless systems don't have memory. Okay? So, if you don't have memory, that means you cannot remember anything. So, if I take those passive components that you have studied so far, resistor, capacitor, and inductor, which one of those cannot store anything? Resistor. Right? So when you take a resistor system, it has no memory. Okay? But when you take a capacitor, it has a way to store energy. Right? So it has memory. Inductor also has memory. Okay? So, when do we say a system is memoryless? Like the system does not have any memory. So a system does not have memory when we apply an input. To be able to compute the output, you're only going to be able to compute the output at the same time. Right? There's no way to compute the output at any other time, like in the future, on the past. Because it does not have memory to remember anything in the past, and does not have any memory to anticipate what's going to happen in the future. So you're only going to be able to compute things at the same time. Right? There's no way you can do past, there's no way you can do future. Right? So the technical definition of the system is that a system is said to be memoryless when the output values can be computed from the input value at the same time. Right? No future, no past. No past. Right? So the key word there is same time. So that means we know that when I have x of t, I push it through the system, and that gives me the output, which is y of t. Y of t will be a function of x of t at the same time. Right? So this, whatever you have in the x will match exactly what you have in the y. Because that's the only way you can compute. Does that make sense? Yeah. Okay. So let me give you concrete examples. So let's say that I have a resistor and I apply a current I of t. So that's my input. This is x of t. And I wanted to find the voltage, which is y of t. So what is the voltage? What is y of t? Ohm's law. So R times I of t, isn't it? Which is R times x of t. So as you can see, the output is computed from the input at the same time. Make sense? Okay, so what about, so that's example one. So let me give you another example, example two. So let's say the mapping is y of t equal to 2x of negative t. What do you say? Has memory, right? Because the output is computed. So, okay, so this is how a C student has done in the past, which I think is clever. So, to check whether the system has memory or not, they will pick three values, right? To pick t equal, so they will pick one negative value, 0, and one positive value. So let's say negative 1. So y of negative 1 is 2 times x of 1, isn't it? So when you look, this is totally different from this. They're not the same. Right? So that just tells you that it has memory. Are you sure? So, and well, if you take t equal to 0, then y of 0, 2 times x of 0. Right? This is misleading because you're going to see this, and then you think that they're the same, so the system is memorized. So that's why they will use three values. Right? So one positive value, one negative value, and a 0. And if all those three are satisfied, then most likely the system is.
So is memory only when it uses a value that came before it, or does it matter if it comes after it too?
No, it's memorized if it's, so if I have like y of 1 give me x of 1, they have to be the same.
Okay. But like if it's y of 1 and x of 2, that is still memory even though x of 2 is in the future.
Yeah.
Okay.
You're not allowed past or future. You only allow present values of the time or both. Put it up.
I got you.
Okay? So when you have this check, but this doesn't check. Right? That shows. So if you're able to find only one instance, like even a single instance, that this thing is not true, I mean the whole thing is not true. You just need to find one. You're able to do. Okay, so they will take t equal to 1 for example, and y of 1 will be 2x of negative 1. Right, so this gives you a future value. This will give you a past value. But we cannot have past or future. We can only have present. Right? So when that's satisfied for all t, positive, negative, and 0, then we say the system is memorized. It has to be true for all t. Okay. So I put a few examples there. So what do you say? Is this memoryless? Yeah? What about this guy?
Yeah.
What about this guy? Yeah. So you only looking at x, right? The rest is a distraction. You're only looking at x. Right? We're not affecting t in the x, right? So we should be fine. So what about this? Yeah? Like I'm saying, everything else is a distraction. Right? We're only looking at the input. But the definition is between the input and the output values at the same time. So this and this are the same, isn't it? Okay. So, now what about this? What about this one? What do you say? Say memberless? So let's check. Let's check whether it's memberless or not. So let's do y of -1 is 5, x of -2. Are they the same? Is this equal to this? No. That right there, that tells you it's not. Are you with me? Okay. So what about this? It has memory. Right? It doesn't? So let's compute y of 0. There. It's x of -3, -5 times x of -5, x of -5. Right? Are you fit? So, like this, and this are different. So it has memory. Okay. So the same thing for discrete time. So I was kind of lazy. I just took the continuous time and I just changed it to make it discrete time. So can you confirm that all the systems are memoryless? Yes.
So if T has a different value on the outputs, it has memory in this case?
Now, so when you have, so let's take a discrete time version. So when you look at this and this, they're the same, right? So whatever value that I'm plugging for, and here is the same value that I'm plugging for x, right? But, so that's true for all this, isn't it?
Yeah.
But whatever value that I'm plugging for x, that's what I will get, right? For y as well. But what about this one? That's not a good example. So let me give you y of n equal to x of 2n. We're changing n in here.
So if it's
So-
x of n minus 2, would it be?
Yeah, it still has memory, right? Because you're changing, right? So if you have this, just pick a value. Let's pick 1, n equal to 1, right? So y of 1 equal to x of maybe 1. Are they the same? What I have inside the square bracket, are they the same? They're not the same. I mean, the system has memory. If it's different, then it has memory. I mean, the system has to remember what happened 1 second before. If it's the same, then it's memory. Yes.
For the cosine one that's above that has no memory, is that just because the cosine n plus 1 would be like a constant?
Yeah, it's just a constant. So if n equal to 1, it's cosine of 2. Right? Cosine of 2 is just a number. Okay? Good question. Any other questions? No? Okay. So let's define causal systems. Let's define causal systems. So when do we say a system is causal? So a system, so Q causal. So when do we say a system is causal? A system is causal if that system, if the output value can be computed from the input value from past and present only, no future values. So the system is able to remember things that happened in the past. That system cannot tell what's going to happen tomorrow. Cannot anticipate what's going to happen. Okay? So, the system said to be causal when the output values at t are computed from the input values at past, so I'll put NR present only. But is it present? Present time only. So the key words are at past and present. Past and present. Right? So no future values are being okay. So only present and past times only. Right? So there should be NR. Okay, so let's look at this. What do you say? It's causal, right? Because t minus 1 is past time value. Right with me? Right, so currently I'm at what time is it? 3:25. 1 second before is 3:24, right? That's the past, isn't it? Okay? So this compared to this is a past time. Are you with me? So this compared to this is a present. Are you with me? Okay. So when a system is memoryless, that means the system is also what? It's causal. Yeah. Right? Because the present is there, included. Right? Okay. So, this and this is past time, isn't it? Okay. So, what about B? What do you say? So when you have t and t plus 1, so when on the time axis, let's say this is t. T plus 1 is where? There, right? It's in the future. Are you think? Yeah. So this is the future one. You all agree with that? Like I said, you can always test this, right? You can use -1, 0, and 1. Isaiah, question? Yeah, okay. You agree? Okay. So what about the last one? What do you say?
Okay.
It's future.
Right, in the future in some cases. Right? So let's do y of -1 is sine of 1 x of -2. So when you look at it, so -1 is there, but -2 is there. Isn't that in the past? That's in the past, right? It's past value of the input. But if I do y of 1 is sine of 3 x of 2. That's a future value. You all agree? Because this one I have 1 here. But I'm requesting the input value at 2, which is a future value. Does that make sense? Yeah? Okay. Alright, so that's a discrete time version of it. Time invariance. That's the third one. Well, the first two are easy. The third one, the fourth, and the fifth one are not so easy. Right? So memories and causality you can just look and tell. But time invariance, you have to prove it. And the fourth one is linearity. You have to prove whether the system is linear. The fifth one is stability. You have to prove that whether the system is stable or not. The very last one, number 6, is whether the system is invertible. So that one is the one that's tedious for students to prove sometimes. And so I don't want to make it harder more than what it is. So we're now going to, I'm going to give you the definition, and we're going to talk about invertibility, which is a property, very important property when you do system identification actually. Right, it turns out to be somehow difficult for the one that to prove sometimes, not all the time. Okay? So, what do we say about time invariance? So a system is time invariant. So maybe I should start with an example. So let's say that I give you close the switch, and you observe the profile of the voltage. It cannot look the same, right? That means the system hasn't changed over time. Are you clear? So the system hasn't varied over time. So it's time invariant. Right? That's what it means. It's time invariant. The system doesn't change over time. Are you clear? Now, so how do we define this technique? Or how do we prove this? How do you prove that? So there's a way to prove it that I'm about to show you. So let's go through the steps to prove time invariance. And the solutions that I write for exam, homework, quizzes all use the same steps. And those are the same steps that I use in the book. So I'm gonna stick to it. And it has always worked for everybody. So I'm just gonna do that. Alright, so step 1. So what do? We take an input, x, for example, which is my V0 in the example that I have above. And we're going to apply that to my system, for example, this RC network. And so I call it system. It doesn't need to be. So it could be any system. It's a way to test whether the system that we have at hand is time invariant or not. So now we're gonna collect the output. We call it y of t. Right. So we are going to adopt this notation where when you apply an input, we call the input x. What we get out of the system, we call it y. Right? The output. Okay. So we take this output and we're gonna apply a delay by t0. So I'm gonna show you this for continuous time, which is the exact same thing for discrete time. And we are going to call this y1 of t. Right? That's the output after the delay. So I'll always, so we call this is y t minus t0. Right? By the delay. Yes. So we call it y1. Now, in step 2, I leave a space here for some reason, but I'm just going to leave it like that. So let's say that I take the same input, x of t, and I am going to wait for 2 years. At t0. And that's x of t minus t0. This is the key. Let's call it a different input. So anytime you change a signal before passing it through a system, call it a different signal. Right? So that's the key. That's the only key to getting this right all the time. Call it a different signal. So G of t, I call it in this case. You can call it whatever you want. So that goes into the system now. And I call this y2. So what just happened? We swap the location of the blocks. Okay? And we are going to observe y2. So if y2 of t equal to y1, so this is y1, this is y2. y2 of t, y1 equal to y2. Then the system is said to be time available. That means if you wait 2 years and come back and simulate the system, you're going to get the output profile is going to be the same. So that's what this means. So that's what step 1 and 2. So let's call it step 2. Then the system is time available. So over the years, I noticed that students are 90% always get this question correct when they do this method. Okay. So the stability one is one student tend not to get correct. Mostly. So you're gonna spend some time on stability. Okay. So let's use this. Let's use a concrete example. Okay. So let's see how we can use this example to prove whether a system is have system. So whether a system is time invariant or not. So I know it's a lot to take in today, right? Today, they talk about a lot of things, especially the properties. As you can see, you see it for yourself, the next homework set. I highly recommend that if you have questions, don't hesitate to find me and ask questions. So I know that at the beginning that this properties are going to now be like totally clear, like how to prove them, but after doing the homework, you'll be pretty solid on this. Okay, so let's do an example. We only have 5 minutes. Okay, so you know what we can do? Let's finish this example. You take a short break, you come, we review the questions, we review a few things about the quiz, and then you can just take the quiz and then. Okay? Alright, so let's do an example. Like, then make sure you fully understand this example. And then if there's a part of it that you don't understand, please don't stop me. And I wanted to make sure that the example that we're about to do, if you take it, if you see it again, and any assignments, you are going to be able to produce exactly what we're talking about. Okay? So let's say that I give you a system, y of t equal to x of at, where a is not equal to 1. Okay, that means time scale. So, can you guess whether this system will be time invariant or not?
Yes.
It's time invariant?
Yes.
Okay, anybody else? So time invariant? Anybody else?
No, because it's not one.
It's not invariant as well.
No, time invariant.
It's not.
Oh, changing your answer.
No, I'm gonna give both answers.
Okay. Anybody else?
It's gonna modifier P.
Yeah, what you said. Yeah, you do this. Oh, okay, you're thinking out loud, okay. That's good. Anybody else? Oh, you don't want to take a stab at this? It's 50-50, right? What?
Function does not
Oh,
exist.
okay, so I don't like to guess, right? So 50-50 is it's not good enough. But you have to be at least 75% sure to guess, right? Okay. So let's just do it. You want me to give you a few minute break first before we do it? What? Just gonna do it? So let's finish it, and then you take a short break, and then solve problem for the quiz. Right? Are you good? All right. So, how do we prove that this system is whether time invariant or not? Okay? So we're gonna do step 1. So step 1. So step 1 says you have x of t. You apply that to the system, and you are going to delay the output. So the output of the system, which is y of t, and we apply that we delay that by t0, and then we call that y1 of t, which is y t minus t0. Okay? So, we know that y of t equal to x of at by definition. That's what you're given, right? Talk to me, over there. So by definition. Right? Are you fit? Okay? So what do you think y of t minus t naught equal to? Is x of what? T minus t naught. So everywhere that I see t, I replace it by t minus t naught, isn't it? Do you see that? Okay, so where say it's not time available? That, so let's prove it. Right, so we have x of at minus a t0. Are you free? So keep your eye on this, that constant. Alright, so let's do step 2. So that is y1. Just complete that. So let's keep that in mind. So let's box it. That's one of the results that we needed. Check whether the system is time of varying or not. Now, so let's do step 2. So step 2. Step 2 says we say pick the system. We swap the delay and the system blocks, which is the delay T0. And so when I push that, the output will be x of t minus t0. Do you agree? Everybody? So we say at this point we have to call this another function. If you miss that step, you're probably going to run into issues. Alright, so now let's apply that as an input to our system now. So by definition of our system, the output will be j of at. Talk to me. So what the system is doing is time scaling the input. By definition, right? That's what we're given. That's what we're given. Are you fixed? So when you take the input, whatever input you apply, you're going to time scale the input to get the output. So here we apply g of t. We're going to time scale g of t. Are you fixed? Yes.
So, from the definition, using the system will always take the input function and scale it?
Yes, time scale. So that's the definition right there. Right? That's what it's doing. When you apply the input, you time scale the input to get the output. Right? That's the definition of the system. Okay. So that's the output of step 2, so we call it y2. Now, we know that y2 of t, right, by definition is g of at. We wanted to express g of t in terms of x of t, to be able to compare it with y1. So we know that g of t is x of t minus t0. What is g of at?
X of at minus t0.
At minus t0. You all agree with that?
Yes.
Take a look at it.
Minus at0.
Yeah, I think, I agree with Jackson.
Oh, minus at0.
Yeah.
Yeah, there should be an A.
So let me give you this example. So let's say f of t equal to t squared plus 2t plus 1. So when I do x of 2t, what do I do? Everywhere that I see t,
Exactly.
I replace it by 2t, isn't it?
Yeah.
So same thing as everything that I see t, I replace it by at. Are you free?
Yes.
Everywhere that I see t, I replace it by at.
But aren't you just saying that t and g of t is equal to t minus t0? So then you would
No, no.
multiply that out.
So g of t is x of t minus t. So let's say t0 equal to 1. Let me give you a concrete example. X of t minus 1. When I can compute x of 2, or g of 2, what is that? Yeah?
That makes sense.
Yes?
On the one above that, g at equal x at minus t naught, why don't you have the 18 naught?
That's what I'm trying to explain. So, this guy is that over there.
Yep.
So whenever you see t, you replace it by the argument in g, right? This like, I always stop at this point, okay? Every semester, because intuitively, if you're not careful, you make mistakes like that. Are you fair?
Yes.
So if I have a g of at, right, whatever I see t, I replace it by at. Make sense? Jackson, you want to present?
No.
Okay, so let's say that I give you f of t equal to t squared plus 2t plus 1, which is t plus 1 squared. Are you okay?
So it's not.
Yeah. So what is the f of 2?
2
2 plus 1 squared.
So 4 plus 4 plus 1. Wait, what?
Are you okay? So whatever here, that's why I replace that.
Oh, okay.
Yeah? Okay. So you are trying to compute the value, right? Look at this as a number. I'm trying to evaluate g at that number. Right? That's why we are going to substitute that in the x. Are you good? So g1 is y1 is this, but y2 is this. X of at minus t0. Are they equal? No, they're not equal. So this system is not time dependent. So if you think about it, you are affecting t. You're changing t, you're scaling t by a number. Right? So that means the system is changing with respect to t. Right? It's not time dependent. Yes?
So then, how come the first one has a time element?
Yeah, so we have the first one with question. So the first one, y of t is x of t and of t0. Isn't it? Oh, no, what is that? The first one is this. So let me write on the side of it. So y of t is x of at. y of t minus t0, yes, goes into where you have CT. You're trying to evaluate the function. Yeah? Now, so I know that this is where I always spend more time when I do time equations. And I always pick this example because that's the one that students always get issues with. So I wanted to make sure that you understand it. Okay, so it gives me x of a. So what about CT? So x of AT minus AT0. So as you can see, x1, y1 and y2 are different. So what conclusion do we draw? The system is not time invariant. Okay? So can you prove that y of t? So I know you have to take a break. So I'm just going to give you this as homework. Can you prove that the system defined by y of t equal to x of t plus just x of t, or 2x of t, for example?
It is time
X of
invariant.
t minus 2. X of t minus 2. What do you say?
Had it before.
It's going to be time invariant.
Yeah. See?
Because you're not affecting t anywhere in this expression. Right? You're not varying, you're not changing t. But so what about this? Y of t equal to, you know what? I think I'm going to give you a graphical example. Yeah?
Push the quiz back next week.
So I'm way over now.
Okay.
So maybe let's do an example, a graphical example on Wednesday. So let me give you a 15-minute break. So you have to find the even and odd, find the energy and all that.
Power zero.
Right?
Power zero.
Yeah, power zero. What about E?
I don't know. Let's see.
Okay, so can we do this? Well, this is a homework question. Should I solve it?
It's one.
It doesn't matter.
One and a half. 2 and a half. 3 and a half. 4 and a half. 5 and a half. 5 and a quarter.
So let's do it. Now, so with this function, can we compute the even? Well, can we compute the? Can we do the even and odd?
Yeah.
So let's compute the even components of this. Now, since we have done the homework, as you said, what do we do? Flip it, right? So that's the origin. So the origin remains. So the data point at -1 comes to 1. This is 0, 1. And the data points at the -2 come to 2. Right? So this is half. Do you agree?
Yep.
So the data point at -3 come to 3, so it's what? The data point at -4 comes to 4. So what is that?
Shouldn't 2 be 3/4?
Hmm?
Oh, that's just.
Yeah, I'm doing x of any given.
I feel for that.
So this will be -1. And then every, is 0 after that. And the data point that was after 1 goes to -1, so what is that? 1. You agree? And the data point that is at 2 goes to -2. That's still 1, isn't it? And the data point, so that was at 3 goes to -3, so half. And the rest are 0. You agree? Okay. So we just need to add this data point together. So SE again. So what are the data points? So at -4, what do I have? -1 plus 0 is -1. Do you agree? At -4. So what about at -3? What about -2? We have. Do you agree? Yes. 1 plus 1/2 is 3/2, isn't it? So what about -1? What about 0? What about at 1? What about at 2? What about 3? What about 4? Okay. So well, if you want the origin, it's right there, isn't it? So as you can see, it's a symmetrical about that. So now we need to divide all the amplitude by 2, right? Alright, so this is x of n plus x of -n. Are you fit? You follow? Oh, any questions? No? Does it make sense? Am I doing it differently than you know, right? Okay. So now we need to divide the amplitude by 2, right? We need to add everything by 2 and 2. Make sense? So what is E infinity of the given component? We get half square, which is what?
1/4.
1/4 plus 9/4 plus 1 plus 1 plus 1. So we can just multiply that by 2. What do you say? Yeah? Okay. Yes.
Should that be 9/16? Does
Uh,
3/4 square?
The 3/4? Oh, 3/4. Yeah, 9/16. So. Thank you. make sense? So just need to add them up, and that's the energy. So the energy is finite. So what about the power? B infinity is 0. Are you free? Okay. So to do the odd, we just take the difference, right? That's the same thing. Take the difference, and then once we have those values, we just square them up and add them up. That will be the odd component energy. Right? And the power for that also will be 0. Okay. So that's question 1.
Quiz?
On the quiz.
He told us that he was gonna do that. He said discrete and continuous, that's it.
This is this.
It's the same thing.
So would it be the same thing or like
So question 2 is continuous.
That's crazy. We're getting divorced.
So question 2. So if you don't get about 90, you pay me $5.
Try to give you $5 now. Good night.
I'll give you 20.
We have a deal, right?
3 of those.
Like
I'll pay your $5 and your $5 and my $5 and hers. Okay. I'll save the phone. Because we're all not gonna give them 90.
number 2. Now number 2. So let's say that I give you x of t equal to
1/80.
what? What is it good for?
What is that?
So t plus 1 plus 2. Let's do minus t.
Wait, it's literally just discrete signals.
That's continuous, right? T minus 4. And the question is, sketch x of t. Can you sketch that?
Yes.
Okay, great. Okay. Alright. Okay, so the next question is y of t is integral from infinity to t
It's fine.
x of tau d tau.
So it's even.
So that's 1. That's 2. Y to 2. So integral from negative infinity to plus infinity.
The one that exists at 4, isn't it?
X of tau d
Just
tau.
at 1.
So in both cases, you're asked to find E infinity for.
Ew.
So find E infinity for this too.
Is it just 1?
6 and 2.
6 and
Oh, 6 and 2?
I thought the x of tau d tau is unit sub.
What?
That's delta d tau? Yeah.
So think about it for a minute. Can you please solve it?
No.
Is that 2 or a Z?
We did this in class.
It's gotta be a Z, right?
No, we did it in class. We did this in class.
But if I get a 50, you guys pay me $5.
I mean, I'm gonna collect a lot of $5.
Yeah.
Can I just give you it now?
I'll prepay.
What's your Venmo?
I'll prepay. If I pass out the semester, I get my $5 back.
With interest.
Yes.
Like one Celsius. Okay.
Yeah, so, can you please calculate this and let me know what you got for the,
Wait, what's your name?
Yeah. And then that's the balance.
Yeah.
What person got this?
Yeah, it was right. It is unit stuff. What's
It is units.
Because you integrate the direct alpha for each one. It is.
Is that a 2 or a 6?
Keys, brother. Come on, man. It's like the square. You know the little rectangle.
Yeah. And then it'll be the
what is this in
You
class?
solve for P and then those are the balance.
It's the rectangle.
And then
It's the
there's one
rectangle.
square up.
Negative 2 to 4.
Yeah, at
What is
one.
the answer? It's integral of direct alpha each time. Never know. Am I usually right?
Not what I studied for.
No, so the balance of the integral will be like negative 2 and
Because I
4.
also know because I'm looking at it right now.
I'm also looking at like an example right now that was like mentioned. So
Ooh, long day.
one day would be A, one by us. So you just like it's gonna be.
So just integrate that.
It's gonna be A, 6. 4 by 72.
Wait, no, you integrate x. So the x from negative 2 to 4. Right.
Right here.
Right there, right? That's the direct. That's the direct.
And then when you do that,
Wait, did I
those
say that?
become that. I took a picture.
Oh, yes, so we did this as an investigation.
Yes,
See?
the balance comes from that, so you're.
That was an investigation right there.
For the integral.
But it wasn't equal. Station.
Oh, because you have one up there.
We did this
Oh,
investigation, right?
Yes.
oh, that's easy.
On January 26th.
Okay, so let's solve it together. So what is the first one equal to? What's y of t equal to? The integral from negative infinity to t.
Zero.
And direct
No, it's gonna be
Unit step.
alright.
So we'll do unit step.
Direct alpha?
What is inside the
These are these how
4 minus.
Tau plus 2 d tau. So it's unit step.
Yeah. You change it.
Because whenever it's tau to tau, it's always unit step. When you integrate it.
So what is this?
Unit step. T minus 2.
T minus
Plus k plus k plus k.
What is that one?
Unit step.
I didn't think that it was of the actual x of t function up there. I thought it was just saying
Yeah,
x
yeah.
of t function.
That's what I really am.
Yeah.
So when we sketch it, what do we have?
Yeah.
From negative 2 to 4. At 1.
And over.
Yeah.
So what is the energy?
6.
6.
Yeah,
One
one
square.
square. One square.
What is p?
0.
Thank you.
Oh, this one. Wait, is this just 0 to 50?
So I need to collect $5 right now before you take it quick.
Okay, we got enough. Don't worry about it.
So,
I got enough.
alright, so let's do y2. What is y2? So integral.
The same thing.
This changes the boundary.
There's something different.
So what is this guy equal to? 1. And what is this guy equal to? What is 1 minus 1? What is e?
So it's not. Okay, so infinity. Yeah, it's infinity.
What is E for this guy?
Zero.
The function is zero, so the energy is zero, isn't it? And the power is zero too. Yes? What?
Oh, so it's one because the value of the unit step is one.
It's literally 1 minus 1 is the answer. I know, I would forget.
No, so when you integrate the delta, that means this is the area, right? Yeah, you find the area and the delta. What is that equal to? 1, isn't it?
Yeah, it is.
What is the area here? So the bounds are fixed, right? The numbers, so we get area. We have T on the bound, then we have U. Right?
Yes.
Make sense?
You got it.
So when the bounds are just numbers, that's the area. Where if one of the bound depends on T, in that case we get unit step function back. So, no, because we have 1 here, and minus 1. 1 minus 1
I told you to do this, right?
Alright, so let me give you one more.
That's crazy. No, it's key.
So what is that?
1 plus 1. There's 2 different integral. There's 2. Integral takes 2. Well, yeah, but there's 2. Yeah, the integral takes 2. Is it infinity? Is it?
So what is
It's
this?
2.
1 plus equal to,
So power 0.
so,
It's unbounded, so it's.
so y of t is what? 2 for all t, isn't it? So what do you think the energy will be? Right? Yeah, great.
Yeah.
What do you think the power is going to be?
1. Power should be. Wait, wouldn't it be 2 over? Yeah, 2 over 2, right?
2.
1.
Power's gonna be 2.
Yeah. Wait.
Is it 2?
I thought it'd be 2 over 2.
How do you get 2?
Because it'll be 2 times 2t over 2t.
What if the 2 t's cancel out?
You forget to square.
4 then.
4.
Please don't forget to square the singles, right? Yeah?
Yeah.
Are you with me?
Wait, so this is makes the entire signal too? Why? But why not?
Yeah,
Why
so-
not the first time?
Integral from negative infinity to plus infinity 4 dt.
Why are you separating?
You integrate, like 4t and then plug in the infinity.
So we're good.
Well, plus infinity.
Yeah.
Are you with me? I don't want to go home sad today. Yes?
So that's the way if we have d of t, if it's like d of tau, we don't do this like
D of tau.
That's alright. I was confident. I'm not confident. Wait, so why was the other one not the same as this?
When the bar depends on t, then you have unit step, right?
yeah.
You have delta.
Like, before this was as two.
But when the bounds are finite, then you're gonna get a number. Either 0 or
But shouldn't it have been 1 plus 1 squared?
Because
Can you go back to the last example? Oh, it's 1 minus 1, that's fine. Okay, yeah, I got it.
The first one was minus.
Yeah, that's fine.
Yes.
What did you say the power was for that power?
The power is 4. Why is there 4? Let's calculate this power. E.
I don't know why is it four.
Wouldn't it be 4
The
times
limit.
e over 2n plus
T
1?
goes to infinity. E infinity.
Watch.
Watch. You agree?
Yes.
No.
So E infinity is
4, so it's really 0.
it's 1.
2 over
No,
t.
so yeah, it's okay. So what is E infinity then? E infinity is the limit
Infinity over
when
infinity.
T goes to infinity of integral from negative T to T for dt, correct?
Yes.
Are you agree?
Yeah.
So that give me 4
What's
T from negative T to T. You agree?
The answer is 4.
Yes.
Yes.
So it's 8T.
Yes. Over 2t.
That's E.
And you will have to call and get paid.
The limit when T goes to infinity,
Watch this. Watch
Wow.
this. I'll write this.
T plus 4T. That's 8T. So the limit of that is infinity. Are you fit? Now, we're going to substitute that in there.
It's over 3. I'll see you next time.
When you're here.
Yeah.
So what do you get?
Apparently 4. What is 18 on 6?
Any other questions?
Partner, okay, what is okay,
So,
What is 18 with
yeah, bring the $5 when you bring the quiz.
yeah, on table it's my favorite. I'm gonna do a partner quiz.
What?
Partner quiz.
Yes.
So we can learn as we go.
So, I think you've seen what is on the quiz already.
Yeah.
So you don't need the process.